Hi everybody, welcome to my Chem 12 YouTube channel. Um, it's a channel that where I'm posting videos to replace the lost instruction that's going on during the COVID pandemic and all the schools are closed. So the idea was to do all kind of what would be classroom instruction on all the different topics in Chemistry 12 at the end of the year, from starting with acid base, which many of you have probably already started. If you've kind of jumped into these videos, chances are you've already begun the acid base unit before we left for spring break. But I felt I would go back to the very beginning and kind of walk through the entire thing. And so I will be continuing to post videos to go to the end of the year. So my plan is to cover all of acid base, then into hydrolysis, then into titration, then into all the reduction oxidation and electrochemistry. So if you subscribe to the channel and turn on your notifications, then you'll get a notification, obviously, when I post a new video that will go on to the next topic. I'm posting them approximately 2 per day. So I'm hoping to have the entire course covered by the end of April. So maybe even before that. That's quite a few. Maybe the middle of April. And so just keep checking in and you'll see that there's the whole series, and they follow a chronological kind of development of a unit as you go through it. It kind of starts with an introduction, and then I go through all the different details. And so we're on an episode now where I've done a whole bunch on the acid-base unit, and we're at the stage now. I think I've only got 2 remaining. So I've got this one, which I believe is episode 11, and it's about amphiprotics, as you can see over my shoulder. And then the next one and the final one of the acid-base unit would be Bronsted-Lowry reactions and a KQ of an overall Bronsted-Lowry reaction. So, and that will be it for the acid base unit. Now, hydrolysis and titration they're tied into acid and base. So you'll see, wow, this isn't really even a new unit. If you kind of pop back in for the hydrolysis videos, yeah, they're all connected to each other. So we do the acid base unit first so that you get a good understanding of what everything is before you move into those other types of kind of side things, the hydrolysis and the titration. For today's video, it's about amphiprotic chemicals. So there's not going to be a whole lot of calculation that's going on with these. It's certainly not at the moment. When I get into the hydrolysis unit, we may get into a little bit more of the calculation, but this is more of a qualitative exploration of amphiprotics. What are they? The concept of, if you have an amphiprotic species, what does it do in water? Will this amphiprotic species make the water acidic or basic? Okay, and you might go, how can something be acidic or basic? Isn't it just one or the other? And you'll kind of see that the definition of an amphiprotic species kind of means that they could potentially be both. So right off the bat, so let's start with, there's 2 things kind of to cover here qualitatively. So number 1, defining and identifying amphiprotic chemicals. So what are we looking for exactly when we're trying to determine if you've even got an amphiprotic chemical, and then take the next step and ask the question, is it going to produce an acidic or basic solution? So over here, I've already pre-written down the definition of an amphiprotic chemical. Now, amphiprotic is actually just a description of a chemical. So it's like saying a tall person. The tall is a description of the person. So amphiprotic, an amphiprotic chemical is giving you a description of the chemical. So amphiprotic is really just an adjective. That's all it is. So it's an adjective describing a chemical that has the ability to gain or lose a proton, an H+. So it can go either way depending on what you mix it with chemically. Okay, so if I happen to take an amphiprotic species and put it into an environment that there's another acid, well, maybe the amphiprotic species will then act as a base. But if I take the amphiprotic species and I put it into an environment that has a different base, then the amphiprotic species may in fact act as an acid. So it can do either. And then we'll look at some of the kind of the identifying features of these chemicals and how do you determine what they're going to do in what scenario. Okay, and there's ways of figuring it out, but we'll kind of walk through this first of all. So the definition, first of all, can either donate an H plus or accept an H plus. Now, if you're going to donate an H plus, that means you must have a hydrogen that is donatable. So you have to have one that you're willing to give up to another chemical. And so you'll find that an amphiprotic species will have a very similar formula to an acid because acids donate H's. So for an amphiprotic species to be that acid part of it, I guess they're all, it's almost like they're multi-personality. So the amphiprotic species, when it's in its acid form, it has to have an H to donate. And so you're going to see that it will have and I'm going to use X for this little video instead of A, just because I don't want you to get confused with the A being acid. So HX. So it will have, X will be some anion, and then H will be a hydrogen covalently bonded to it. I probably shouldn't even say it's an anion, but H is covalently bonded to whatever X is. Now, that just looks like the formula of an acid, correct? So that's what you're going to see. Now it might be H2X, it might be H3X, it might be anything. What is unique about an amphiprotic species, though, is that it also has the ability to act as a base. So not only does it have an H and can donate it, it has the ability to act as a base as well. Which means, what types of chemicals, if you think back to the definition of a base, what could you see in the formula of a base that allowed you to understand that it was in fact a base? Well, the primary thing that you should be looking for is you should be looking for a negative charge. So if it's an anion, then it has the ability to pick up an H. So if this formula has an H, it can be an acid. But if it has a negative charge, and that could be -2, it could be -3, whatever it could be a base. So typically what you're looking for with amphiprotic chemicals is you're looking for a donatable H, like an H out on the left, and a negative charge. So you're looking for both of those things in the formula. And so you're typically looking for an anion that has also a donatable H. And there's several different examples of that. Certainly on the Ka table, you can go down the left-hand side of the Ka table, and you can see numerous examples of a chemical that has a negative charge, but it also has an H, and that's why it's on the Ka table. So let's give you a couple of examples here. So if you look on the table, you'll see chemicals such as H, C2O4 -1. So there's a donatable H, and there's the negative charge. So that's hydrogen oxalate. That is an amphiprotic species because it has an H and it has a negative charge. How about H2C6H5O7? Negative charge. So that's dihydrogen citrate. So it actually has 2 H's. It's diprotic, and it has a negative charge. So it's got both those properties of a base and an acid. Okay, so that is an amphiprotic species. Okay. How about H3PO4? Has H's, can be an acid. Does it have the properties of a base? No, it's neutral, and it's not a nitrogen compound. So it is neutral, it can't be a base. So if that didn't have a negative charge, which it doesn't. It's not a base. So this is not amphiprotic. That would just be a plain old acid. Okay, so that's phosphoric acid. So you're looking for negative charge and hydrogens. And how many hydrogens doesn't really matter. How about this one? Probably seen that one before. That is the anion acetate. It's got a negative charge. Great, that acts as a base. And looks like it has hydrogens. But I said, and I use a descriptor right at the very beginning, it has to have a donatable hydrogen. Now, you might say, well, it's got hydrogens, so aren't they donatable? Some hydrogens are really not donatable, and the reason why they're not is because they're not part of a polar bond. H's that are part of a polar covalent bond can be donatable. You can pop them off really easily. When it's a non-polar bond, they don't pop off really easily. It's like the covalent bond is too strong, so you can't pull them off. So this thing is an organic compound. So let me draw it just to show you. So here's the C. There's one H, two H's, three H's. Then it goes to that C, double bonded O, and that has, whoops. That's where the negative charge is. So these three hydrogens that are here, they are covalently bonded to the carbon. And if you recall back to Chem 11 and trying to determine if you have a polar bond or not, hydrogen and carbon, their differences in electronegativity are not very big. So this is a non-polar bond. Those hydrogens don't pop off really easily. So these guys are not donatable. Yes, acetate has hydrogens, but no, they're not donatable. Which means that even though when you first look at it, it's got, okay, negative charge base, hydrogen's cool. It's amphiprotic. It's not. Those are not donatable hydrogens. So this is not amphiprotic. Two more examples to show you here. How about this one? Hydrogen sulfate. So hydrogen sulfate, negative charge. Great. Hydrogen over here in the acid, and it's in that that typical acid position. So this is a donatable hydrogen. It has a negative charge. It looks on the surface anyways that it has all those properties of being amphiprotic. So it can certainly donate that H. Okay, and this one is, you might be asking right after the last one, well, how am I supposed to know if the hydrogens are donatable? If the hydrogens aren't the first thing in the list, then it typically isn't a donatable hydrogen. So you'll notice in that last one that I wrote, the hydrogens come after the carbon, like you're writing them in the formula after the carbon, which is an indication that they're attached to a carbon and they're not polar bonds. They're not donatable. They're not acidic hydrogens, as it were. Typically, an acidic hydrogen is going to be written out in front or at the end of that COO, and then it will have an H afterwards. Okay, so that's kind of how you tell. It's a fairly simplistic explanation, but that's kind of what you're looking for. Certainly in Chem 12, that's enough information to go on. So you've got a hydrogen out here that can be donated. This thing can definitely be an acid. It's got a negative charge. It certainly looks like it can be a base. But remember that rule, not all anions are necessarily bases. There are 6, which are the conjugates of strong acids. And if you had your Ka table out, if you have your Ka table out, the 6 in the gray area, okay, so those 6 there, all 6 of them. So perchlorate, iodide, bromide, chloride, nitrate, and hydrogen sulfate. They are all over here on the right-hand side. The arrow is going 100% towards them, which means 0% going back the other way. And when it's a 0%, that means none. which means that this guy here cannot pick up a hydrogen from anything to go back to forming H2SO4, which means it doesn't act as a base. So even though it's got on the surface, it's got the properties of an amphiprotic thing, it can only be an acid. It cannot be a base because it's the conjugate of a strong acid. So this guy is not amphiprotic. Okay, and so that's one that's a tricky one. And yes, you're probably going to be asked at some point in your chemistry career if this is an amphiprotic chemical, and the answer is no, it's an acid. It's never a base, so cannot be a base, conjugate of a strong acid, so that's not one. And then how about the last one that I want to show you? And you can probably already tell that I'm kind of going through the tricks, so your guess would probably be this is not amphiprotic, and your guess would be right, it's not amphiprotic. So why isn't it amphiprotic? Because it's got H's, it kind of looks like they can be donated. And not only that, NH3 is down here, it's on the Ka table. You can even find it over here on the left-hand side, on the acid side. And NH3 is also on the base side, like it's right up there. So it's actually on the base side as well. So it can pick up an H and form NH4, and it's over here on this side. However, if you look really close at this table, and I'm not sure you can see it, it's kind of small for me just holding it up, but if you've got your own Ka table, look really closely at it. On the Ka table, that's the equation that's there. The arrows go in the opposite direction, like it's going 100% that way, which means 0% in the forward direction, which means as an acid, NH3 has 0% of the molecules acting as an acid, which means even though NH3 can act as a base, it cannot act as an acid, and therefore it's not amphiprotic. Okay, so there are two very typical ones that are asked of you. Is this an amphiprotic species? HSO4 minus, looks like it, but it's not. HSO4 minus does not act as a base. It is the conjugate of a strong acid. And the second one is NH3. NH3 can act as a base, but NH3 does not act as an acid, therefore it's not amphiprotic. Okay, so everything, and kind of the rule of thumb is, everything that you can find on both sides of this Ka table, if you can find it on the weak side for the acids, and you can find it on the base side, in the weak section, like in the between the two shaded sections, if you can find it on both sides, it is amphiprotic. Okay, so it's just kind of a rule of thumb if you happen to have it with you. Now, the second question up here is, or not question, but second thing I want to go over in terms of amphiprotic is, okay, so if you throw it into water, will it make the solution acidic or basic? Next video, or next class, is going to go into the, okay, so what will it do when you combine it with other acids and bases? But we're going to talk specifically with water. So if I take an amphiprotic chemical and put it into water, what does it do? And how can you prove that you know what it does? So as an example, let's take, I'm going to put a question up here just to frame it. So will a solution of HCO3 minus be acidic or basic at 25 degrees Celsius? So HCO3 minus, so that is bicarbonate or hydrogen carbonate, as it were. And you look at it and you say to yourself, okay, so HCO3 minus, that has a hydrogen on the left-hand side. It can be an acid. And it's got a negative charge, and it's not the conjugate of a strong acid. So HCO3 minus has both acidic and basic properties, certainly in the formula and on the surface. So to answer this question, what you're going to do is you are going to say to yourself, okay, so if HCO3 minus is acting as an acid, the strength with which it does that, kind of like if you're talking about relative comparisons between it as an acid and it as a base, the numerical value that tells you that is its equilibrium constant, because an equilibrium constant is kind of telling you, if you throw it into water, here's the proportion of how many products get made to how many reactants you have at equilibrium. And so it tells you kind of how well it makes products, for long story short. So if you compare the value of Ka to its Kb, those are two equilibrium constants. Their actual numerical value will tell you which one it prefers doing. Okay, so it bumps into water molecules. Does it prefer to donate an H, or does it prefer to receive an H? What does it do? So what you're doing is you're going the Ka of HCO3 minus equals, and that's just off the table, right? So I pull out my table and I find, and be very careful where you're looking, because you don't want to go down the wrong side of the table. Because you're talking about HCO3 minus being an acid, you look down the left-hand side for where it's an acid. So you go down, you go down, you go down, and you find it's pretty low. So I'm going to guess this thing has trouble being an acid. So HCO3 minus as an acid is right down there. Ka is 5.6 times 10 to the negative 11 at 25 degrees, and that's what I asked. So that's its Ka. So that gives you a relative sense of how well it makes the products of it being an acid. So then you want to know what its Kb is. So its Kb equals, and it takes a little bit more doing, because Kb, if you recall from when we were just doing the weak bases, the Kb of any base is equal to Kw divided by the Ka of its conjugate acid. So to determine its conjugate acid, and we haven't even written an equation, but to determine its conjugate acid, you put an H back on it. Like if it acted as a base, it would pick up an H and form something. So if HCO3 minus picked up an H, it would form H2CO3. So its conjugate acid is H2CO3, which is on the table. So 1.0 times 10 to the negative 14 is Kw, and then the Ka, not of itself, of its conjugate. So H2CO3 is right here, and it is 4.3 times 10 to the negative 7. 4.3 times 10 to the negative 7, which equals some number. So let's quickly pop that into the calculator. 1 times 10 to the negative 14 divided by 4.3 times 10 to the negative 7, and you're going to get 2.3 times 10, 1, 2, 3, 4, 5, 6, 7, 8, 10 to the negative 8. So it's those two numbers that you compare. So to answer this question, Kb is, well, I would say significantly bigger than Ka, therefore makes a basic solution. So whenever you're asked that question, okay, this chemical, you put it in water, does it make the solution acidic or basic? And it's an amphiprotic chemical. You're looking at its own Ka versus its own Kb, and that tells you kind of what it does. Now, to take that a step further, to kind of explain a little more, you can kind of see that the Kb is approximately, because it's 10 to the negative 8, and its Ka is 10 to the negative 11. I know it's 2.3 and 5.6, but whatever, 10 to the negative 8 and 10 to the negative 11. So that's about a difference of 10 to the third, which is 1,000. So it's about 1,000 times better as a base than it is an acid. Now this is a critical thing to be contemplating. It's 1,000 times better as a base than it is an acid, which doesn't say it's not an acid. It just says it's better. It's 1,000 times better at being an acid. So think of it this way, for this exact chemical. If you throw 1,000 HCO3 minuses into water, for every one of them that acts as an acid, approximately, ballpark figure, 999 of them act as a base. Approximately. Okay, so just to give you a sense that it's not as if the HCO3 minuses, dump them into water, they never act as an acid. Some of them do. It's just that the massive majority of them act as a base. There's a whole bunch of thermodynamic reasons why, but generally speaking, that's the way you think about it. So the base reaction of HCO3 minus completely overwhelms and dominates over the acid reaction of HCO3 minus. And therefore the solution comes out basic overall, because the poor little ones acting as an acid just kind of get overwhelmed by the ones acting as the base. So what you need to have in your mind, and this will be, we'll bring this up in the next class as well, is something known as the predominant reaction. When you take HCO3 minus and put it into water, the predominant reaction is HCO3 minus acting as a base over HCO3 minus acting as an acid. Okay, so keep that in mind, and that should cover us for amphiprotic species. You notice I didn't go into any kind of calculations for pH or anything like that, because sometimes there is that proportion kind of messes up what the final pH will be. So that's not really part of the Chem 12 curriculum. It's more of a qualitative thing when you're talking about amphiprotic chemicals. Okay, so that's amphiprotic species. And next class will be our final class of the acid-base unit before we proceed into hydrolysis. And that class will be about Bronsted-Lowry equations and the equilibrium constant of a Bronsted-Lowry equation. So, don't forget that to subscribe to the channel, and when you do that and turn on your notifications, you'll see the videos pop up in your notifications as I produce them, and then you can kind of follow along for the rest of Chemistry 12 and just kind of slowly go through the course as I go through the course, or as I would go through the course if I happen to be sitting in my school right now with my Chem 12s in front of me. We'd be doing these things. Obviously, the number one thing that we're missing right now is obviously we can't do the lab component, which I'm very sad about because that's a big part of chemistry. However, I want you to learn what you can learn. So subscribe to the channel, share this with everybody you know in Chem 12. Spread the word that these videos are out there and they can help with understanding the different topics of Chem 12. And I'll see you next class for the final video of the acid-base unit. See you later.